Good day and welcome to Big Bad Tech. I'm Instructor Jim Pytel, and today's topic of discussion is an introduction to renewable energy. Our objective is to perform a brief introduction to a subset of the various forms of renewable energy being used for industrial and small-scale electrical power generation. Specifically, we'll take a quick look at wind, hydro, and solar and discuss the features and advantages and disadvantages of these renewable resources. A couple housekeeping notes before we begin regarding the intended audience and the scope of this and related lectures. Bottom line up front, renewable energy technicians are electromechanical technicians, and these lectures on renewable energy are not intended for the average dimwit bebopping down the street, but rather viewers with the necessary background and working understanding of energy, power, efficiency, capacity factor, DC circuit analysis, single-phase AC circuit analysis, three-phase AC circuit analysis, the three dimensions of AC power, apparent, real, and reactive, power factor correction, transformers, mechanics, hydraulics, switches, sensors, hardwire, relay-based ladder logic and motor control, programmable logic controller or PLCs, digital logic, industrial control, power electronics applications like rectifiers and inverters, batteries, power transmission, and motors and generators. If there is the slightest hesitancy on your part about any of these subjects, by all means revisit the supporting content in the Big Bad Tech channel, because when I discuss renewable energy, I'm operating on the understanding that we're all on the same page regarding electromechanical technology, and we are moving forward from this agreed upon start point with all of these tools in your toolbox. This being said, if you're a little rusty on any of these topics or feel a little overwhelmed, don't worry, I got you. Because as specific topics come up in the course of this discussion, I'll try to point you to the correct lecture or playlist that explores that specific topic of interest in greater detail. Regarding the scope of this and related lectures, we will examine solely the electromechanical concepts of renewable energy, not chemistry, biology, economics, politics, nor public policy. This means I'm not going to go into a lot of great detail about the chemical reactions in biofuel processing, nor discuss the economic impacts of production tax credits. But when it comes to something like the electromechanical aspects of wind turbine blade pitching mechanisms, quite like Teddy Roosevelt and his stupid bears, I'm going to talk your ears off. I do need to place special emphasis on the rules of engagement regarding politics, since for some inexplicable reason, renewable energy has entered the oh-so-productive culture war. If you want to talk politics, go right ahead, but don't do it here. Go shout at an Arby's clerk. This is the internet, after all, and we need to keep it free from sensationalism and be polite to one another as its founders intended. I will not engage in political discussions, and neither should you, because you can't out crazy, and there is some cray stuff out there that has no basis in reality. Renewable energy is not a government conspiracy to take away your guns and turn you into a gay. Trust me, I've worked for the government before, and they are straight up not that smart nor that organized to pull off a scheme of such complexity and dubious worth. Renewable energy is happening, whether you like it or not, largely because it's driven by economics. Let me ask you this question. What is the price of fossil fuel-based non-renewable resources like gas done over the course of your lifetime? Yes, there are short-term fluctuations up and down due to market volatility, but long-term, inevitably, the price of gas has gone up and it is not going to go down. More people siphoning off more gallons from an increasingly less accessible pool of limited resources. You do the math. It's simple supply and demand. The reality is the price of fossil fuel-based non-renewable resources has gotten to the point that installing and maintaining renewable energy facilities is becoming cost competitive. Yes, renewable energy installations cost money to install. They require regular maintenance, have inefficiencies, and have negative impacts just like every other power station out there. But the fuel is free. You know renewable energy is the real deal when big banks and multinational oil and gas companies make huge investments in it because they recognize the future of renewable energy is profitable. The long-term price of fuel is just one aspect affecting supply and demand economics. From the demand side, consider large new customers requiring copious amounts of electricity, like data centers, crypto mining operations, and AI, and perhaps most critically, the electrification of transportation. Switching from a petroleum-powered transportation infrastructure to an electric-powered one will be a fundamental change to business as usual and will place a heavy new demand for electricity. From the supply side, consider that the planned retirement of numerous coal and gas power plants will remove these producers from the supply. Additionally, consider the impacts of the increased frequency and intensity of extreme heat events and wildfires that interfere with the generation and transmission of electrical power. As demand increases and supply decreases, the slope of the supply and demand curve only gets steeper and steeper, and renewable energy makes more and more economic and practical sense. Lest you become too enthused, let me inform you that renewable energy is not magic, and one preferred source cannot immediately solve all of our problems overnight. Solar power is not the solution. Wind power is not the solution, nor is hydro, biomass, nor geothermal power in isolation. All these sources taken together, including natural gas for an interim period or even small modular nuclear reactors, and the necessary means of efficiently transmitting and storing these diverse energy sources are. A non-technical associate of mine perhaps put it best. Think of every energy source as a piece of Swiss cheese with obvious holes that prevent reliance on that single source. Take another piece of Swiss cheese with its own holes in different locations and overlay it on top. Less holes appear in the layered mass. Add more layers, and pretty soon there's no holes. A more diverse energy portfolio might ultimately be cheaper, more reliable, and more secure, but it will take time, investment, and an educated workforce to make it happen. It won't be easy to build, it won't be simple to manage, and I never said it would be. By virtue of watching this lecture, I'm presuming you are interested in becoming part of that educated workforce and the new energy future, rather than just bitching about how hard and complicated it's going to be. So let us begin. We should probably start with some necessary definitions. First, let's differentiate between non-renewable and renewable resources and identify a couple examples of each. A non-renewable resource is some resource that is finite or limited in quantity and not replenished within our lifespan, meaning what you got is what you get, and you ain't getting any more, so tough luck if you use it all and had no backup plans. Coal, oil, and natural gas are examples of non-renewable resources because there is simply a limited finite amount of these fossil fuels available, and it's not cost effective to raise a dinosaur from a hatchling to adulthood, only to kill it, bury it, hopefully in a more convenient and accessible location, and wait till the combined heat and pressure of the earth turns it into a usable petroleum product. By the same definition, we should also consider nuclear a non-renewable resource, since within our lifetime there's no chance of being resupplied with nuclear fuel, and although there's a substantial amount of it out there, it's still a finite quantity. A renewable resource, in contrast, is continually replenished by ongoing natural phenomenon. Solar, wind, hydro, biomass, and geothermal are renewable resources because these resources have, are, and will continue to exist for the conceivable duration of humanity's future, whether we use them or not. Renewable resources don't run out and are cyclically replaced in perpetuity. Let's now differentiate between dispatchable and non-dispatchable resources. Dispatchable generation refers to power sources that can be started, stopped, and adjusted by grid operators to match electrical power supply with electrical power demand. Examples of dispatchable generation includes coal-fired power plants, natural gas plants, geothermal plants, and large hydroelectric facilities that can quickly ramp up or down depending upon the grid's needs. A nuclear power plant is also considered dispatchable. However, they're not exactly the most responsive of beasts and can take a long time to bring up to full capacity. Non-dispatchable generation, in contrast, refers to power sources that cannot be started, stopped, or adjusted at will due to factors that cannot be controlled. Non-dispatchable resources tend to be intermittent, which means they're not continuously available, and can disappear as suddenly as they appear, and variable, which means their intensity isn't constant and can spike up or down due to factors out of our control. Examples of non-dispatchable generation include solar and wind, both of which are highly dependent upon the weather. I should note that non-dispatchable does not mean unpredictable. Admittedly, we don't own nor can we control the weather yet. We can, however, predict the weather to a reasonable degree of accuracy and take this into account when forecasting fuel requirements for the near future. With a diverse portfolio of resources at your disposal, you can make use of cheap and plentiful renewable resources when they're available and only resort to more expensive non-renewable resources when they're not. Like I said earlier, economics is largely driving this fundamental change. Here's a plot of energy generation by source for a period in early spring 2024. You'll note natural gas generation in tan experiences a dip. Why? Well, take a look at wind power in green. It's peaking. If we zoom into a period towards the end of March, you can see some pretty predictable behavior. Solar in yellow peaks and valleys as the sun rises and sets, with changes in intensity from one day to the next. Nuclear power is steady as a rock. Coal, hydro, and natural gas ramp up and down as electrical demand peaks during the day and valleys at night. When free renewable wind power peaks, non-renewable natural gas turbines back off. This balancing act is not without its complications, though, since, as I mentioned earlier, non-dispatchable resources can be highly variable in nature. Imagine a sudden, unanticipated ramp-up in demand in which large numbers of customers suddenly need more power, accompanied simultaneously by a sudden unplanned ramp down in supply, when a regional weather event suddenly flatlines the outputs of large numbers of solar and wind farms. Too much demand, not enough supply, and it all happens too quick. As we learned in the Power Generation, Transmission, and Use lecture, way back in the DC Electrical Circuit Analysis playlist, available at the Big Bad Tech channel, the grid is a just-in-time delivery system, meaning instantaneous power supply must at all times match instantaneous power demand, and lacking energy storage, which we'll discuss in a moment, any imbalance between the two can mean catastrophic failure. Consider the opposite scenario, a ramp down in demand accompanied by a sudden simultaneous weather-induced ramp up in supply, where all the solar and wind farms are at peak capacity. Too much power and nowhere to send it. Without any load to direct this power, this output needs to be curtailed, which is essentially turning off excess generation to meet low demand. Lacking storage, curtailment represents a lost opportunity because all that free renewable power is essentially going to waste. These scenarios illustrate the fundamental requirements towards developing an all-renewable grid. In addition to generation from renewable resources, we need to consider storage, transmission, efficiency, and effective, intelligent management. Energy storage. During periods of high supply and low demand, free renewable energy can be stored in pumped hydro facilities, batteries, flywheels, compressed air facilities, and or converted into and stored as a combustible gas like hydrogen. During periods of low supply and high demand, these stored resources can be drawn down to balance input and output. Lacking storage in all renewable grid will be unreliable and unworkable because solar only works when it's sunny and wind only works when it's windy. Transmission. A modern transmission system would allow the export of free renewable energy from regions experiencing high output and low demand to those regions experiencing low output and high demand. Long story short, it may not be sunny or windy at your house right now, but it is sunny and windy somewhere. Efficient interconnection between distant regions allows those regions to share excess production with their neighbors and rely on those distant neighbors in times of need. Additionally, the most productive sources of renewable power tend to be some distance from where the power is actually used. To get that free renewable power across the barren wastelands where it's generated, to the shoe-wearing regions of the country where it's used, you need a modern transmission system. We'll examine high-voltage DC transmission in later lectures, which enables efficient power transfer from point to point over long distances. Efficiency. Viewers will recall that more efficient devices use less energy to accomplish the same task. A society using more efficient devices does not need to generate as much power, since less power is directed towards losses. Intelligent management. We'll explore smart grid applications in later lectures. However, one component of the smart grid is known as load shifting, which starts or stops an electrical load as a function of supply. Consider a smart appliance like a dishwasher. Load the smart dishwasher before you go to sleep or go to work, and you press start. You don't care when the dishes get washed as long as they get washed before you wake up or you get home from work. The smart dishwasher sits there and waits and waits and waits until there's a lot of inexpensive renewable power in the grid, and then and only then starts the cycle, thus freeing the utility from resorting to more expensive non-renewable resources. Now that we've got some basic definitions and concepts out of the way, let's take a closer look at the different types of renewable energy on an introductory level. You'll note this lecture largely concerns itself with the production of electrical power from renewable resources rather than the direct use or use as energy storage. Perhaps one of the greatest advantages of an electrical power grid is that electrical power can be so easily converted to other forms at the point of use, some distance away from the initial source. For example, if a warm house is your intended goal, one could directly burn wood, a form of biomass, in a wood stove. One could also appropriately site your house such that it experiences longer periods of passive solar exposure, or if you live in a geothermally active area, directly pipe geothermally heated water through a radiator. Using these renewable resources in this direct fashion results in the desired outcome of heat with no intermediate conversion stage. Wood biomass to heat, sun to heat, geothermal to heat. Problem is, not everyone has a wood stove, not everyone's house is properly sited to take advantage of passive solar heating, and not everyone lives on top of a geothermal hotspot like those shy and reserved inbred blonde elves that populate Iceland. For this reason, resources are often converted into another form, typically electricity prior to being used. Biomass to electricity to heat. Solar to electricity to heat. Geothermal to electricity to heat. To be sure, there are losses in this two-stage conversion of these resources, but it sure beats having no heat at all. Historically, electrical power generation has involved some prime mover using a turbine to turn the rotor of a generator to export electrical power for use. A prime mover is some outside mechanical power source that could take the form of expanding steam, falling water, or moving wind. In this fashion, the mechanical power of the prime mover is converted into electrical power. For example, a coal-fired power plant burns coal to heat water in a boiler to produce high-pressure steam that forces a turbine to rotate. The rotating turbine turns a generator, which produces electricity. Historically, coal-fired power plants served as baseload power production. However, over time, coal's share of electrical power production has steadily decreased. A nuclear power plant operates similarly in that the heat of nuclear fission heats water in a boiler to produce high-pressure steam that forces a turbine to rotate. The rotating turbine again turns a generator, which produces electricity. As with coal, a nuclear power plant can serve as a reliable baseload power plant, although it's not the most responsive of beasts and sometimes struggles to track rapidly changing demand conditions. Combustion-style natural gas turbines operate slightly differently in that natural gas along with a stream of air is combusted and heat from the combustion itself causes the turbine to rotate. As with other systems, the rotating turbine turns a generator, which produces electricity. Natural gas plants are sufficiently responsive enough to be used as base and peaking power plants, i.e. plants brought online or disconnected at a short notice. Energy production from these non-renewable resources is reliable and dispatchable, but not without attendant disadvantages beyond their inherent non-renewable, i.e. finite nature. Coal-fired power plants are a source of CO2 and particulate emissions. Natural gas has significantly less particulate emissions and only emits about half the CO2 as coal, but it's not benign in any sense. Nuclear, in contrast, produces no CO2 emissions at all. However, spent fuel is considered radioactive waste that must be safely stored. For this and other reasons, renewable resources like hydropower, including wave and tidal energy, solar power, including PV solar and concentrated solar power, wind power, biomass, and geothermal are now considered as serious alternatives. You note I consciously try to avoid using the buzzwords clean or green when discussing renewable power, since they mean different things to different interest groups and are so overused and misapplied from everything from clean coal to green laundry detergent, they've largely lost any meaning to society. Now, before we dive into this clean and green list, I want to be upfront about the scope of this series. As fascinating as wave, tidal, concentrated solar power, biomass, and geothermal power stations may be, I probably won't discuss them in any greater detail beyond this briefest of brief introductions, and instead reserve future lectures for detailed technical discussions on wind, hydro, and solar PV for two very important reasons. Reason one, I do not have the same level of experience with wave, tidal, concentrating solar power, biomass, and geothermal power as I do with wind, hydro, and solar PV. Reason two, wind, hydro, and solar PV are where the jobs are at. I'm not saying there's no jobs in wave, tidal, concentrating solar power, biomass, or geothermal, but I am saying there's lots of jobs in wind, hydro, and solar PV, and this is where you need to focus your efforts on, at least initially. In keeping with this spirit, realize I'll be concentrating on large-scale industrial applications of renewable energy that can get you a job, rather than small-scale residential or off-grid applications, at least initially. Let us begin. Hydro. Hydropower harnesses the force of moving water to generate electricity. Hydropower is a renewable resource because it depends upon the water cycle, which replenishes our rivers from the snow and rain every year. Typical hydropower facilities include a dam that backs up the water to help control the river's flow. The reservoirs behind a dam are generally of one of two types, storage or run-of-the-river. As the name implies, a storage project uses a reservoir that stores a sufficient capacity of water for use when electricity demand is high, whereas a run-of-the-river project operates with minimal or no water storage. The simple diagram of a hydropower facility includes a reservoir, a dam, an inlet, a penstock, a turbine, a generator, a powerhouse, and an outlet. The dam backs up river water. The inlet directs pressurized flow into a penstock, which is essentially a pipe or a conduit used to carry water to a turbine. The turbine, of which there are two major types, a Kaplan, which looks like the bladed propeller of an airplane or a boat, and the Francis, which is a reaction-style turbine that works on fluid pressure changes as water moves through it. The turbine is typically mounted to a vertical shaft which spins the generator inside the powerhouse. Finally, the outlet serves to expel water from the turbine downstream. By the way, a real hydropower facility is a lot more complicated than this simple diagram suggests. There are a number of accessory components like wicket gates that open and close to keep pressure and flow, thus torque and rotational speed of the turbine and generator inside desired specifications. We'll examine industrial applications of hydropower production in greater detail in later lectures. I should note there are numerous alternate configurations for hydropower facilities and turbines that are often reflective of scale, head, and flow for a particular site. A popular design for smaller hydropower facilities is a Pelton wheel style turbine, which uses a nozzle to direct pressurized flow onto a wheel with buckets, called impulse blades affixed to the perimeter. Hydropower has advantages and disadvantages. Hydropower produces no CO2 nor particulate emissions. Being renewable and inexhaustible, hydropower is inexpensive. Finally, since water flows at all times, day and night, hydropower is dispatchable and reliable because it's not intermittent nor variable, at least in the short term. This being said, the startup costs for a hydropower facility are astronomically expensive. And I'm not sure if you notice this or not, hydropower has a nasty habit of inundating entire river valleys and all the trees, towns, animals, and archaeological treasures in these valleys under tons of water, not to mention altering fish migration patterns. Long story short, a dam and reservoir is a destructive beast that fundamentally alters the ecosystem in which it is built. Additionally, hydropower is very site-specific and subject to long-term drought conditions. Lest you think hydropower facilities be confined to rivers, there's an ocean of opportunity out there, including wave and tidal energy. Wave energy systems come in all sorts of crazy configurations, including point absorber buoys, surface attenuators, oscillating water columns, and overtopping devices. These different configurations convert wave energy into either airflow, water flow, or the relative motion between two bodies, and these forces are then converted to electrical power. Tidal power systems, in contrast, make use of daily tidal fluctuations, a result of the gravitational interaction between the Earth and the Moon, to generate power. Certain tidal power stations open a gate in a dam to allow a basin to fill with water during high tide, and as the tide recedes, the outgoing water is routed through a turbine, generating electricity.